combined battery demo that has both the EIS and the pulsed loads in one software. The pulsed load test, as we had before, is meant for a destructive test of a primary cell that just repeats the same pulses over and over again until the battery is depleted. This was designed to simulate the loads that a customer's device might put on the battery, and therefore test those batteries in a real-life simulation. And now you can see here, as it's doing this pulse test, it's generating a current profile on all of the cells in that test fixture simultaneously and recording the voltage and current draw. It is at the same time calculating the capacity removed from the cell with each pulse. And this kind of test can be run for days or even, many hours at a time. Some customers are even using a 2-day test and just ending that test when all the cells go below a certain voltage threshold. So with that technique, they can validate whether this battery type can survive in their devices as long as they hope that it will. So this loops over and over again. They can test several trays in the same lot, but I'm just going to stop that test right there. And it calculated the statistics for both the tray and the lot. But like I said, we just added a EIS test option to this tester as well. And we're going to be testing now some rechargeable nickel metal hydride cells using a combined test that's going to do both a pulse test and an EIS test. To do that, I'm going to change some settings here and change to a different test profile. While I'm here in these settings, this tester has a lot of additional features built in here. You saw there's a log in, log out that can record who's doing what test. And so there's a user administrator that would allow user credentials to be entered there. There is a software integrity scheme just to provide protection from anyone tampering with any of the files that are used to control the test. There's also a hardware integrity system that will make sure that the correct hardware is connected and that it's not out of calibration. And in that pulse test system, there's also a profile editor, which allows the user to configure the kind of pulses that are being tested there. This will allow definition of those pulses in terms of ramps and holds at particular current set points. And it also allows the sampling rate to be increased at periods of greater interest, so that, for instance, in these sharp transitions, we could collect more samples at a higher rate and see what's happening without generating terabytes and terabytes of data for every battery test that we want to run. So that's some of the settings that are in here. I've just saved here to a new test profile that we're going to run on some rechargeable cells. But Prior to doing that, we will want to do a zero adjust routine on our fixture. For that, we have a special circuit board that we're going to insert into the fixture, and that provides a 0 point for each channel to calibrate so that the system can subtract off the impedance of all of the cables and probes and simply give you then the resulting impedances of the cell during the EIS test. So I'll kick off the zero adjust routine right here. I have to put that little board in the fixture, and I'll hit continue there, and then that will run a sweep from 2 kilohertz on down to 1/10 of a hertz. Well, that's going to take a little while, so I'm going to accelerate this portion of the video a little bit, and after that's done, I'll show you how we install the batteries themselves and kick those off. Okay, so our zero adjust routine has completed. Now we simply take out that zero adjust circuit board and load in the rechargeable cells that we want to test. And then I'm going to run this combined test, which is going to do first the EIS and then do a parallel pulse test on all the cells. I'll enter in a lot number here. Click next. It's starting to collect the EIS data on the first cell. As with a lot of EIS tests, we start at the higher frequencies first. So the points seem to come faster at the beginning, and then they get slower as we reach the lower frequencies. The reason, of course, is that we want to measure several complete cycles of that frequency, and with a lower frequency, it just takes longer to complete a cycle. So it's starting at the high frequencies, going down to a lower frequency, and then it's sweeping through each position one at a time. That's because the measurement is actually done with the PXI SMU, switch to each cell position one at a time. Okay, at any point there, I could have aborted the test just by hitting here. And then it just finished the EIS portion, and it is starting up the pulsed load. For this one, we had a slightly different current profile that we defined in our profile editor, loading all 8 cells in parallel. And again, this is set up to do, there's about a minute's worth of pulses, but in normal operation, this could be run for hours and hours until the cells are depleted. I think that's about all there is there. It's going to do these pulses. I should mention, currently this can do 50 milliamp pulses on both of these cell types. We've used it up to 500 milliamp pulses on other cells before. And then for the EIS, the SMU could do probably up to 2 amps, 60 volts So there's quite a bit of flexibility of testing different battery types with similar hardware. That's it. Reached the end of the test. Instead of starting another tray, I'll just cancel here, and then you can see the overlay of all those EIS curves of all 8 cells in parallel. That looks pretty typical. There's a few differences between the cells, but um, they all have a nice clean response. And it would save that data to files that you could then analyze with other software. And really that's the heart of EIS, is collecting those curves and then statistically looking at it and seeing what they tell you about the batteries. So there it is, a combination of a load pulse load tester and button cell EIS in one fixture.